So last time in the last class we learned about tensor algebra, and we learned to how to deal with second order tensors. Now today's class will learn how to look at higher order tensors. And I think the basic definition of tensors that I had given last time, it was clear that it's for an nth order tensor, when you operate it on a vector, you get an n minus 1th order tensor. And now if you have a third order tensor, in that case, you will get, when you operate it on a vector v, you get a tensor, second order tensor t. And it's a linear mapping. That means b operating on a linear combination of a1, v1 would give you a linear combination of the resultant vectors like this. This is true for every a comma b belonging to the real numbers, and for v1 and v2 belonging to vector spaces, some vector space. And here we are dealing with all three spaces. We are dealing with real spaces only. The components the same way that we had written for a second order tensor, you can write a third order tensor in it sort of in this form. We write Bijk as Ei tensor Ej tensor Ek. So these are the three the different components based on the repeated index will give you the third order tensor V. Now when you operate the third order tensor on a vector V, you would be writing it as Bijk Ei tensor Ejk operating on Bl El, writing V in terms of its component, in terms of the basis vectors. So now when you operate, just like you did with the second order tensor, you take Ek and El and take the dot product, and what you're left with is the second order tensor Ei tensor Ej. Bl is a scalar, so you bring it outside. You have Bijk Bl sitting there. Ekl becomes delta Kl, so you have Bijk Bl delta Kl Ei tensor Ej. As you can see, this is the ijth component then. And K is transferred here, so you get Bijk Vk Ei tensor Ej. So this becomes a second order tensor. So the components of the second order tensor now would be given by Bijk Vk. Now if you consider this particular expression where a third order tensor is operating on a vector En, basis vector En, and then the resultant second order tensor will operate on Em, and that will give us a vector finally, and then that will take dot product with the El vector. So writing the innermost expression that we have figured out here, that's what it's going to be. So it will be Bijk Ei tensor Ej delta Nk. When you operate second order tensor on this vector Em, you would get El dot Bijk delta Kn delta Jm vector Ei. And then you will take the dot product between El and Ei. What you're left with is Bijk delta Il delta Jm delta Kn. You transfer the index, you will get Blmn. That's the resultant of this expression. This tells you that this is the Lmn component of the tensor, of a third order tensor. An example of a third order tensor is the permutation tensor that we had seen. And this is how you will write this. You write the third order tensor in this form. Now, similarly, just like what we did with the third order tensor, you can define an nth order tensor, fourth order, fifth order tensor. You can define the components of this vector C, let's say, will be Ci1, Ci2, I1, I2, I3, In, and then you have I1 tensor, Ei2 tensor, Ei3, and so on, the n times tensor product, where the values of these quantities I1, I2, and I3 will be one of these, 1, 2, 3. So the total number of components then you can say is, this can take I1, I2, I1 as 1, 2, 3, I2 as 1, 2, 3, and so on. So you have n times such combinations will give you total number of components as 3 to the power n. So if you have a fourth order tensor, the way you have when you would write a constitutive relationship between stress and strain or stress and strain rate, you would have 3 to the power 4 terms, which is 81. So, because you're relating Cij with a tensorCijkl with a second order tensor epsilon kl. So all components of sigma ij, if you assume they depend on all components of kl, then you would require 81 terms to define this linear relationship, and that's done by using a fourth order tensor. Now, in certain applications, you might have to change the basis of the tensor. So you are writing the tensor as EI tensor EJ, and in place of that, now you want to use some other basis which is also orthogonal. So in both these bases are orthonormal, but it's a different basis which might be convenient for certain problem. So you want to convert the tensor into this basis. Now, by rotation or whichever means. So now, say the basis is changed using a transformation Q. That means you now vector x that was written in the EI basis will be written as Q times x bar prime in the EI prime basis, E prime basis. And the new basis is also orthogonal, and let's say the vectors are given by E1 prime, E2 prime, and E3 prime. That means uh, this transformation is transforming E1 vector to something given by Q times E1. It's coming from here. And E2 as, so you're writing it as Q times E1 prime, Q times E2 prime, Q times Q operating on E3 prime. So now from here you have built this relationship that E1 is essentially Q times E1 prime, E2 is Q times E2 prime, and E3 is Q operating on E3 prime. Now combining in the matrix form, we are writing it as E1, E2, E3. We're calling it S1, let's say, and Q is here operating on E1 prime, E2 prime, E3 prime. So you form a matrix equation like this. Now, because the column these are all, both of them are orthonormal basis, that means they're orthogonal vectors. And any matrix formed with its columns as orthonormal would give you an orthogonal matrix. That means, which means that S1 transpose is S inverse, S1 inverse. S2 transpose is S2 inverse, which means if you take from this expression, if you take S2 inverse, writing is as S2 inverse, that will give you Q, which can be written as in this form as S1 S2 transpose, which is Q. Now, if you look at Q into Q transpose, you will see they have S1 S2 transpose, S1 S2 transpose, and if you take that, you will have S2 transpose becoming S2 and S1 becoming S1 transpose. Now S2 transpose into S2 is identity tensor, that goes away, and now you're left with S1 and S1 transpose. S1 is also an orthogonal matrix, so you get identity. That means Q into Q transpose is identity, which implies that Q transpose is Q inverse. So Q is also an orthogonal matrix. So what we get is, the result that we get is, if you have an orthogonal matrix multiplying another orthogonal matrix, and the resultant matrix will also be orthogonal. So now we have shown that Q is an orthogonal matrix. Now what is the form of it? What are the components of this Q? That's what we want to check. Can we write it in terms of EI and EI's and EI primes? So let's say we are writing EI bar, this is the equation that we had written previously, is EI is essentially Q times EI prime. Now if we take the form as EK, tensor EK prime, we see that immediately this will give you EK prime dot with EI will give you delta KI, and this vector becomes the resultant vector EK. Now there's a transfer of index would happen, and it will become EI vector, which means that now we have identified the form of Q. So Q is essentially EK tensor EK prime. Okay, that's the form. Now, to get the components, what you do is we use this form. Qij will be essentially EI dot Q operating on EJ. This is same as the way we had written components Tij in the previous class. So now Q has this form EK tensor EK prime operating on EJ. So you get EK prime dot EJ, and then you have EI dot EK coming through, and then you have which becomes delta KI. Now that is delta Ki, and this thing is Ek prime dot Ej. Now there's a transfer of index that will happen, so you'll write this as Ei prime Ej, which as we have seen is essentially Qij. So we have identified the components of Q. Now, if we just the same way that we write a vector U in terms of its basis vectors Ej, we have the component U dot Ej, and this is not a dot product, but this is just so these are the components. So now same way we can write Ei prime in terms of the basis Ej. So the new basis vectors you can write it in terms of the old basis vectors. So we'll have Ei prime Ej dot Ej, which is coming from here, just the same way, which is nothing but, as we had seen, Ei prime dot Ej is Qij, so we replace it with that. So you have established that Ei prime is nothing but it is Qij Ej r. Okay, that's what it was supposed to be. Same way you can write Ei in terms of Ej prime, so a vector Ei from the older basis in terms of the new basis vectors. And this will be the form. This is nothing but the transpose of that. That's Qji. So Ei is essentially Qji Ej prime. That's Q transpose. Now taking that, we can sort of write this as the vector V as Q transpose V prime. Let's say in terms of this V prime essentially is Ej prime Vi Q transpose. And U prime then would be Ui Ej prime times Q transpose. So that's what has happened. Now, if you had a mapping using a second order tensor T, which is mapping V to U, that will become something like this. So we are multiplying both sides by Q, so you get Q times U, which is U prime, and then this V can be written in terms of V prime as Q transpose V prime. So now you have obtained the new new mapping that you have from V prime to U prime is essentially given by Qt Q transpose, which is this. So the components of this mapping at Tij or T bar Ij are essentially Qik, Tkl, and Q transpose of Lj. Now Q transpose of Lj can be written as Qjl. So you have the component of T bar Ij as Qik, Qjl, Tkl. That's the change of basis will change the mapping also. So this is how it will change. Now T, the original second order tensor, now you can write it in this form, which is in the basis vectors Ei prime and Ej prime. Okay. So eventually you'll get Tij prime as we have seen is this, which is Qik, Qjl, and Tkl Ei tensor Ej. Now you can you can write this as Qik Ei prime, and this you can send it. These are all scalars, so you can do this operation. So you have Qik Ei prime and Qjl Ej prime, which are nothing but you have Ek tensor El, and the component is Tkl, which is nothing but T. Right. So that's what you get. So this gives you change of basis. Now we can move to the next topic, which is on tensor calculus. So now we know how to manipulate tensors. We've taken care of tensor algebra essentially. Now we look at what can be said about the differentiation. Now let's say if we revise our basic definition of differentiation. Your qt, let's say there's a function phi which is a function of t. Then you can write d phi dt as phi evaluated at a small time, at a time t plus delta t, subtract phi t from it, and then you evaluate this quantity in the limit of delta t going to 0. So now, if we consider a vector exactly the same way, so if it has vectors, the components of the vectors are function of time, because basis you have chosen, which may, if it is a function of time, then it will also be, uh, you'll have to worry about the derivative of the components again in terms of this basis, which might be changing with time. For example, rotating frame of reference. But for now, we'll stick to only the basis fixed and only the components are a function of time. Now, if you want to take derivative of this vector dv dt, that will be in the limit delta t going to 0. You are evaluating a small change in the vector components with that small change in delta t in the limit of delta t going to 0. That gives you dvi dt. Each component is varying in a certain way of time, and the derivative of that vector would be dvi dt ei. Similarly, for a second order tensor, let's say if you have the components, the basis vectors are not changing with time, only the components are changing with time. So then the derivative with respect to time or whatever quantity scalar t can be written as the component derivative, and this doesn't change, EI tensor doesn't change. So if you write it in the matrix form, let's say you have AT, BT, CT and DT as some matrix, let's say A of T, then you can write DA, DT as individual components going sort of having derivatives with respect to time. This is what it will mean. So that's what so all components are differentiated. So this is when we have scalar functions, the vectors and tensors and scalar, when they are functions of scalar variable, then that's how you will take the derivative. But suppose if they're functions of vector, let's say if a scalar is a function of some vector x, which is same as saying that phi depends on its components x1, x2, and x3 in a certain way, right? Now, if you change the components of the vector by a small amount, let's say in the direction u. So what you're doing is you had the vector here x, and then you have another vector, let's say u, in this direction. You are changing by a small amount. So you're essentially adding some small vector alpha u, and the new vector x will be given by this quantity. So now you are evaluating the quantity phi at x was the value here. Now at this new location, you have a value phi of x plus u bar. And you want to see how it varies as a function of this change in this direction. So you look at small change delta phi, which is if you move from x to x plus u, which you can write as in terms of components, you can write as x1, x2 plus u1, u2, and so on, minus phi evaluated at different points. So all this time you should think of them, it's very convenient to think of them in this fashion. Essentially writing phi as a function of x1 plus u1, x2 plus u2, x3 plus u3, minus phi at x1, x2, and x3. That's how you can, that's an easy way of seeing this. Now the variation we want to say is in u1, u2, u3. The only thing is that u1, u2, u3, the way you are writing it, you are interested in a certain vector u. So these quantities u1, u2, u3 can be small, but then they would be small in that direction. They would be proportional to each other. So u2 by u1 and u3 by u2 will be constant, some constant. Now let's say you're writing u as we discussed as x prime, which is x plus alpha times u. So in a certain direction, which can have, let's say, you can choose it to be normalized vector with length unity, but you're scaling with a small number alpha. So alpha is a small number, a small scalar or small number. Okay, now you want to write the small change in phi as you go from x to x prime. This you can evaluate, you can define. Now we are defining this derivative d phi in the direction u as limit alpha tending to 0 as you are, suppose if you were pointing here, this was the x vector and then you made a small change in this vector in this direction. So this is the u direction and you made a small change of alpha u. So as you take this direction, in this direction, you go infinitesimal quantity. If you just want to step in that direction, what will be the change that you expect in phi? This you can evaluate by defining this derivative with respect to alpha 10, and then you say alpha tending to 0, right? So this is same as you're moving from a location x1, x2 to, let's say, x1. This is for the two-dimensional thing. Space, and you're moving to x1 plus alpha u1 and x2 plus alpha u2. That's what it means. So the way you will write the derivative would be this way. So let's say if we choose u to be in the direction of x. So if we choose it to be in the direction of x, then you'll write d of phi on u as d of phi in the direction of e1. And that would imply that you're taking essentially, because phi was a function of x1, x2, you're essentially taking only in the direction of x1. And that's given by del phi del x1 e1. This is called, this way of writing the entire derivative in a certain direction is called as a directional derivative. So if it gives you a change in the scalar or rate of change in a scalar as you move in a certain direction. So this is a directional derivative. It's called a Getue derivative as well. That's the name that you will see some places. Now we can instead of looking at these individually in certain directions, you can write this quantity. You can define this quantity d of phi, which you like a vector having a vector form of this type del phi del x1, and now it is understandable that it's in the direction e1, and this change is in the direction e2. This is called a Frecce derivative. Okay, these are just the names given. So from here, once you know this, you can operate it on u direction. In this case, that operation would be a dot product between two vectors. D of phi is a vector operating dot with another vector u1. That will give you specifically del phi del u in the direction u. That's the Getue derivative directly in the direction u. Now let's take an example. Let's take a function phi, which is, let's say, a sine function of the norm of the vector. This is norm square, right? So this is norm square. It depends on that. So x belongs to an R3 space. So you can write this vector in the initial notation we can write this as xi xi. So if you expand, you will be sine of x1 square, x2 square, x3 square. That's what the function phi is. But it's a function of vector x. So you can take the first component del phi del x1. You can differentiate this. You'll get cos of xi xi and 2 times x1. Similarly, del phi del x2 would be 2 times x2 cos this, and del phi del x3 would be 2 times x3. Putting together, you will get the Frecce derivative d phi as 2 times x1, 2 times x2, x3. You can write this as 2 times x vector cos of xi xi. This is nothing but what you call as gradient of phi. So what you define is gradient of phi. You call this as gradient of phi. Okay. So this quantity that you have started with, this quantity is nothing but grad of phi. This is the notation that we use for gradient, inverted triangle. Now you can have a scalar function which is a function of a second order tensor. If that is the case, it just simply means just the way we have when we had phi of x as phi of x1, x2, x3 in terms of the component. Same way, a scalar function of a tensor would mean that it's a function of all the components t11, t12, and so on. Now, if you make a small change to the tensor, let's say we make a change to tensor t prime is t plus u. If you make that change, then you can write a small change in phi corresponding to that would be phi t prime minus phi t, which will be given by this. Now, you can think of these changes as changing one by one each component by a certain amount. So t11 is changing by u prime 1 1 and so on. So this change, if you let's say write it in the Taylor series expansion, you can write this as del phi del t11 u11 prime so on, and plus what you would have is order these terms, square terms. These are negligible. Let's say if you are making these changes such that u11 goes to 0 and u12 goes to 0. That's how. So you can write the same thing that what we did with the vector. You can in this case you are writing it as a small change that you're making to all the tensor components by a certain amount alpha. If you write it in the limit alpha going to 0, this quantity phi t prime minus phi t divided by alpha in the limit alpha going to 0, if you write this, then you have what you end up getting is this quantity, which is d phi dt, d phi of the tensor t operating on another tensor u, giving you these quantities, which are all scalars, by the way, as you can see. And as you would notice, this is essentially, you can think of them as, let's say I didn't define this double product between two tensors, but this double dot between two tensors essentially means aij, bij. So that's what this double dot means. So if you use this definition, then we can write this quantity that we have obtained in this form. Del phi del t double dot with u. Now from here, you can notice that the ijth component of, and now you notice that this is a tensor because it has all the components corresponding to a tensor. So you can write this as del phi del t11, del phi del t12, del phi del t13, and so on here also. So I just skipped this portion and I like this only t31. And this will be del 3, t33. So you can write this tensor. So the ijth component of this tensor would be given by del phi t, del phi by del tij. Now, if we take an example of a function which is a scalar, the best example, sort of an easy example, would be trace of t. One can take determinant of t also, which is a scalar function of phi, which is a scalar function of a second order tensor. Now, if we take trace as the thing, then we know that trace is given by t11 plus t22 plus t33. That means the del phi del t11 is 1, del phi del t12 is 0, and so on. So you can write del phi del t as now as, if you put it in the component form, you get diagonal elements as 1, and all the off diagonal terms, because there is no terms here in the definition of trace, they went to 0. Clearly you can see determinant would be slightly more complicated to write, but you can write it the same way. It's doable, of course. So now moving on, let's say if we talked about a scalar being a function of a vector. Now let's take a vector being a function of another vector. So we can think of it as a field of, like on an x sort of a vector plane. We're defining these vectors. Let's say the v, which is another vector, which is a function of this vector x. So v being a vector, again an R3 vector, and also a function of R3 vector, will be given by v1x, v2x. These are the three components that you have. Now these are scalars, of course, and we can just use the same concepts that we use for scalars for these parts individually. Correct? So let's say if you look at variation in v1, we'll write variation v1 as a function of position. You can think of x as a position or any other vector. Then small change that you make to the vector x can be written in this form v1 x bar, and then remaining you can think of it as Taylor series expansion based on this kind of a function multivariable definition, multivariable function. So now you have this, plus you have higher order terms. Similarly, you can write the component v2 in this form and v3 also. Now, if we say that delta x1, delta x2, delta x3 are not really arbitrary, three different arbitrary numbers as you would consider them to be if they were truly multivariate functions, the way you deal with them. But they're related. So let's say if you want to go in a direction u, and you are making a small step, taking a small step in that. That means delta x is in the direction u, and the small number is alpha by which you are moving in the direction. So each component would be scaled by that. Now, to denote that, we will write this as the ith component. What is the change? So this, if you think of vi as phi, then you know exactly what to write. That will be same. So you'll get the derivative, the form for the ith component of vector v in this form, and this will give you uh, del phi I del xj uj. So in the ith component, as you make a step in the j direction, what is the change that you perceive? We choose to write this this quantity as grad of v. So this is gradient of the vector, grad of v. If you choose to write that, now you can treat it as a tensor operating on a vector u. So you can write this grad v as del vi del xj ei tensor ej. So it's a second order tensor. So grad v is a second order tensor. Trace of grad v is del vi del xi, the diagonal components of this tensor, and which we define as divergence of p. So this gives you divergence of p, which for different quantities it will have some physical significance. Now, if you consider a second order gradient of a second order tensor with as you move in space as a function of x vector, it can be space vector or any other vector. So t is a function of x. So now if you take that, you can take it again in the component wise, just the way we sort of we break the way we have broken it down, the vector variation in the vector with respect to another vector. Same way, we also break down how each component of the tensor will vary as you make a small change in the vector x. So in the expanded form, you can write this as del ti del x1, delta x1, del tij del x2, delta x2, and so on, and then higher order terms. Now writing again as delta x as a small change in a certain direction, that is like a get-to derivative that we mentioned, you have this quantity, ij quantity would be x plus alpha u, and this is that, divided by alpha. In the limit of alpha going to 0, all the higher order terms will go to 0, and what you will be left with would be del tij del xk uk. This you can think of as a third order tensor operating on a vector. So you can write it in this form. Grad t ijk ei tensor ej tensor ek operating on uk, which is same as this quantity. So if you take a gradient of a second order tensor, you get a third order tensor. And the components of that tensor are del tij del xk ei tensor ej tensor ek. That's how I write it. So now, if you divergence of a second order tensor, if you have to define, this is the definition. Okay, just keep in mind this is how we have defined it. There could be reasons for this definition, but this is how you define it. You say that the divergence of a second order tensor is essentially defined as if you take a dot product with in the direction with a u vector. Some u is any arbitrary vector from a vector space. That should be equal to divergence of the transpose of the second order tensor operating on the vector u. That's how it is defined. So once you take the definition, that's how you'll stick to it. So then you can define your divergence of T as Tij xj. That's how it will come about to be. So now stress is some quantity. I mean, just if you want to understand, because we wanted to take divergence here, let's look at divergence of a stress, right? So let's say there is a stress tensor sigma. We consider this component which is in the n direction uh, on this surface which has normal in the n direction. Then you can write sigma operating on n will give you the traction force on that surface. You can take any. So if sigma is defined here, then you can draw a plane. You can say in the direction in the defining the normal to this plane is n. Then the force, if it's a stress, if sigma is a stress, then will be given by sigma n. So this sigma n will be the direction of the force. So of course it will have components. Uh, T would have components in the normal direction. Let me write this as n cap. Uh, then there would be a component in the tangential direction 1, and there would be a component in the tangential direction 2. So this is how you can break stress. Now let's say if we take this representative volume, and let's say it is aligned, the surfaces are aligned with one of the axes. The normal is aligned with one of the axes. In this case, if we look at this surface, then the x-axis is what the normal is aligned with. So you say sigma, the traction that is acting, the net traction that is acting on this surface, let's say minus the traction, because it's here, it's going to act in the opposite direction, because n is minus I cap and this is plus I cap. So you can write this as sigma at x plus delta x operating on n cap, which is I cap for this, multiplied by area. This gives you the force. Similarly, the sigma acting on the j direction multiplied by dAy, this gives you the direction, the magnitude of the total traction that is acting on the in the j cap, not in the j cap direction, on the surface aligned with the uh, which has normal as the j cap. Same way you can have the k cap direction also. This is DAC. Okay, so the net force then will be given by, if you take this quantity, you can write this as del sigma del I cap. Then you have del sigma del y. This is the net tensor, and then you have del sigma del z. So the second order uh, tensor undergoing derivative in the x direction here, y direction here, and z direction here. So the net quantity, then you will write this as delta grad of t I cap, because you're taking the derivative in the x direction. So from this definition that we had defined, grad of t in the u cap direction would be grad of t, u cap is here I, and this is the outside I, correct? Then this part would be the grad of t j, and this is j cap, this is grad of t, this is k cap. Oh, sorry, this, because of the z, it's k cap, and this k cap is standing outside. And this delta v that we had as a volume, we shift it to down here and write this as a per unit volume force or body force. Then putting together, you can write this entire expression as grad T EL operating on EL. So grad T IJ K EI tensor EJ K tensor EL, and then you have operating on EL. This is a third order tensor, so that's how you write this. And you get the quantity del T IJ del XJ EI. This you choose to define as your divergence of stress, which gives you the body force. So, and apparently this way of defining it, this gives you this definition, which eventually leads to this kind of a thing. It respects this. So that's how you define the divergence. Now, of course, there are other kind of derivatives that we can take. Let's say we define these quantities. We are going to define these spatial quantities. For example, Laplacian. What is a Laplacian? You take divergence of gradient of phi is called Laplacian. It can denote this. No, if we take grad of phi, if you can write in the component form as del phi del xi ei, and then you take divergence of this vector, that will be del 2 phi del xi del xi. So derivative in the I direction. That is the derivative. So that's what we had defined. Del dot p is del vi del xi, and that's what this is. This is del 2 phi del xi del xi. So this second order derivative, you can write this as, you can denote this by Laplacian by Nabla square. This is the Nabla operator. You can say Nabla square phi. If you expand this, you will see this is essentially del 2 phi del x1 square, del 2 phi del x2 square plus del 2 phi del x3 square. Is what this is written. This is your Laplacian grad phi, and that's how you denote it. Now, gradient of a scalar. So instead of looking at the Laplacian, if you take just gradient of gradient, then it will be essentially grad of phi is a vector. Now you take gradient of a vector, which will give you a second order tensor. So gradient of phi is del phi I del xi ei, and this is the ith component. So we can write the vector tensor as del vi del xj ei tensor ej. So if we follow this definition, where vi is the ith component here, we will get del phi del xi del xj, which is this quantity, and then you have ei tensor ej. So you get del 2 phi del xi del xj ei tensor ej. So that gives you a second order tensor. So grad of grad is second order tensor, and you don't write this as grad square. Grad square is reserved for Laplacian. Now Laplacian of a vector, if you take divergence of gradient of a vector v, that's the way we took divergence of gradient of phi. Now you have gradient of vector v, and you take divergence of that. This is of course a second order tensor, so this is del dot t. So we'll have to use the definition that we have defined for divergence of a second order tensor. So grad of phi, as we had seen, is written as del vi del xj ei tensor ej. Now you want to take derivative of that. As we had seen earlier, you had defined this as del tij del xj as the divergence. So del dot t, you had defined, that definition was this for the divergence of a second order tensor. So using this definition, we know this is ej, so that gives you xj here, and this is your tij. So del dot del by del xj of del vi del xj, and now the direction is given by ei. So this is ei. So this gives you a vector. Okay. So Laplacian of a vector is a vector. Laplacian of a scalar is a scalar. Laplacian of a second order tensor, if you look at, which is going to be divergence of the third order tensor, which will be del ti del xj ei tensor ej tensor ek, would be written as del 2 ti del xk del xk ei tensor ej. So divergent Laplacian of a second order tensor would be, we can write this as del square t. T is a tensor, and this we can write this as del square of vector v. Now, if you would see, these are nothing but you have del 2 t11, del x1, del x1, e1 tensor e1, plus so on. So all of them are defined this way. So so del 2 t11 del x2 e1 tensor e1. So each of the components will have all the derivatives. That's what it means. So if you look at the Laplacian of a second order tensor, if I can expand and write here, it will be something like del 2 T11 del. I can just choose a different notation. So instead of writing T11 several times over, I can write this as this. This is del 2 del y or del x2 square plus del 2 del x3 square operating on T11. And similarly, you would have this operator del 2, this gradient operator operating on T12. So all the components are having the same, are undergoing the same operator, Laplacian operator. So you can write this as Laplacian operator on T11. So you can write this as grad square of T11. This is grad square of T12, grad square of T21, square of T31, and so on. That'll give you Laplacian of a second order tensor. Now we'll just to learn how to do manipulations when you have uh, gradients involved, we'll do some problems and then I think we'll stop. So if you look at gradient of a scalar, the curl of a gradient of a scalar, then we'll write this as, I think I have not defined the curl. So before this, let me define the curl. So let's say, anyway, so this is what we want to do, curl of a gradient. So grad phi is, we know, is del phi del xj ej or del phi del xi ei. The same thing. Repeated index means they summed over. So whether you write it as I or j doesn't matter. So now to define the curl of a vector, we can define the curl. This is the definition of the curl. So curl of vector is, if you take, let's say, omega cross u is essentially grad of V minus grad of V transpose. As you can see, this is an antisymmetric tensor operating on U. So you can think of it as W operating on U. Now, going back of the concepts that we had discussed regarding anti-symmetric tensors or skew-symmetric tensors, we said W of U is associated always and always an associated vector with which you can define that, and that's called the axial vector thing. So curl is essentially the axial vector of the skew tensor grad V minus grad V transpose, and you can see that this is a skew transpose because if you take transpose of this grad V minus grad V transpose, to take transpose you will get grad of V minus grad of V transpose minus grad of V, which is minus times grad V minus grad V transpose. So which means that W is transpose is minus W, which is the definition for skew symmetric tensors. Now going by this definition, we know that now that the curl of V is the axial vector of a skew symmetric tensor. Okay. So now curl of V, but curl of V we can define as now as a curl of VK. We write the vector V in terms of its components, and then we say it is del VK del xj ej. So grad you can write as del xj ej, and then that will give you del VK del xj ej cross product with ek. Ej cross product with ek can be written as epsilon ijk ei. So this gives you the curl of V. So curl of V is given by this quantity del Vk del xj epsilon ijk ei. Now let's look at curl of a gradient. So curl of a gradient means that you have Vk is essentially del phi del xk. You're taking derivative with respect to j, so you have xj, and you have epsilon ijk ei. Now because phi is a continuous function, and so we can sort of change. So if it's differentiable, then you can sort of interchange the differentiation order. You can write this as del 2 phi del xj del xk ei epsilon ijk. Now, instead of writing j as k and k as j, here we have not changed exchange. Here we are exchanging the order. Now we are saying that if we change k to j, just here we are just choosing to write it as wherever you see j, you are changing it to k, and wherever you see k, you are changing it to j. So when you make this change, this epsilon ijk becomes epsilon ikj, and xj becomes xk, and xk becomes xj. Now you see, now we use that definition that del2 phi del xk del xj is same as del2 phi del xj del xk. But because you have swapped these two indices, that means you have not respected the circular that ijk permutation. That means you have interchange. So epsilon ikj is essentially minus epsilon ijk, and this is same. This is negative of. So these two are minus times. So it's essentially, let's say, if this is a and this is minus a, this would imply that a is 0. So you can see that the same quantity is negative of itself, which means that it must be 0, which gives you curl of gradient of a scalar vector, scalar function is 0. Now, curl of a tensor can also be defined. It's a definition, of course. We're defining it. So curl of a tensor is defined as something which is operating on U, and it's curl of T transpose U. So you define a vector. You have T vector. You take a U vector which is just any vector from the vector space V. Then you operate T transpose on U and take a curl of on that. That's how you define the curl of T also. Now, in the expanded form, the curl of T would look like curl of T T J K. This is the transpose you're writing. T J K E K tensor E J operating on U. Now U dot E J will give you U J. This is T J K and this is E K. So this is T transpose U you have written as T J K U J E K. Now you're taking a curl with that. That means you will take the kth component here as tjkuj, differentiate with m, you will get em cross product with ek, and you are interested in the ith component. So you'll get the ith component as del t jk. Uj is a constant vector that you have chosen, so you can pull it out of the derivative. So it's aside here. You have del t jk del xm epsilon imk ei. So this is the component of the vector in the ith direction. Now you can see that the curl of a tensor is essentially also a tensor. Second order tensor is also a second order tensor. So now the components of that second order tensor can be defined by these. Curl of the ijth component would be del t jk del xm epsilon imk. So this is how you can define the curl of a tensor. This is the definition that we used. Now, some manipulations with the curls, you can just, these are very useful. You will find them. For example, this often appears in Navier-Stokes when you want to modify the convective terms. They appear there. So you'll encounter them very often when you're dealing with your, for example, Navier-Stokes. So now curl of a vector, let's say we define curl of that vector as W. Now we write curl of W as del, of course I'm writing the ith component of this as del omega k del x del omega k del xj epsilon ijk. I can also write this as curl of W as I can repeat the index and write it in the basis vector epsilon ijk ei. So these two are equivalent ways. You take the ith component or you write it in the basis vectors. So anyway, the curl of W, the ith component is given by this. Now, what is WK? WK will be the kth component of the curl of U. That will be del UL del XM epsilon KML, K component ML. This is coming from the definition that we had used previously, defined previously. Now, epsilon ijk sits outside, epsilon kml is here, and these are both constant tensors, so you can be pulled aside out of the derivatives. And then inside the derivative, you have del 2 ul, del xj, del xm, which is coming from here. Now this quantity, which has a repeated index, epsilon kml and epsilon kij, you have seen this can be written in terms of, in the previous class, in terms of delta, in the canonical delta. So we write as we had seen earlier. So this expression is delta mi delta lj, delta mi delta j, and then you take minus times delta mj and delta li. That's what this is. And it's multiplied by this. Now we can transfer the index here. You can see that m becomes I. So this m becomes I here, and j becomes L. So this L or L becomes J. So we change L to J. So we have this quantity. This together gives you this. So del 2 UL becomes del 2 UJ, del XJ, del XI. And this quantity comes where L will become I, so it become L becomes UI, del 2 UI, and then J becomes M, so del XJ, del XM becomes del XM, del XM. Now this we have seen, this is the Laplacian, right? So this is essentially del square of the vector U, and this is the ith component. And this is the, if you can split it as del uj del xj, and then you take del by del xi of that, this will become the ith component of, this is divergence of course, so this is del dot u, so this is del dot u, and then you're taking a gradient of that, which is given by xi, and then you taking the ith component of this. So now we have shown that the curl of u is essentially gradient of the divergence of u minus times Laplacian of the vector u. Let's take this third identity, which is divergence of a cross product u cross v. You can show that it's essentially you will have to transfer it. So when you take you can write this as v dot of curl of u minus u dot of curl of u. This is very interesting. So let's look at how it comes about. And the curl of the u cross v essentially is uj vk epsilon ijk ei that we had seen earlier in the previous class. Now ei is a constant vector, the basis vector, it's constant, and epsilon ijk is also constant. So you can just pull out. And when you take divergence of this, this will be with respect to, this is essentially del dot some vector wi ei. That will be same as wi del xi. So this can be written as that. So when we write this in the initial notation, if you take the divergence, then you get del uj vk del xi epsilon ijk. Now what we do is we say, okay, let's sort of use the chain rule. Now we can write this expression as del uj del xi multiplied by vk plus uj del vk del xi, right? So we split it into two pieces like this, and we say this is matching. This is j. So this you can sort of rearrange this thing as epsilon kij, and if you do that, you get the definition of the curl of u. So curl of u vector would be del u j del xi epsilon kij ek is what it's going to be. So and vk can be written as of course vk can be written as v dot ek. So now we pull out V and we write the VK here. So this becomes your curl of U. This is V dot curl of U. Similarly, exactly the same way, you can work on this part. Here the thing is you have Uj and epsilon ijk, and there'll be k del xi. So you want the free index to be as j, because then you can take dot product with it. So now if you define this quantity, you can write this quantity as del vk del xi epsilon, and if you want to write this as j, and you have jki, that's how you can write this, and then you have uj. This is one way. Now you can write uj as u dot ej, so you will have del vk del xi epsilon j ki u dot ej. So you pull out the u, so you have finally the quantity that you're left with is u dot with del vk del xi epsilon j ki ej. This would, you would have called it a curl, but then the indices have to be reversed, have to be swapped. So you write them as u dot del vk del xi epsilon j I k e j. Now, of course, when you have swapped, you get a negative sign. Now, this thing, what is remaining here, this quantity without the minus sign is your curl of v. So when you put it back there, you get this expression. So interestingly, you get divergence of u cross v as divergence of u cross v is given by v dot curl of u and u dot v curl of v minus times that. This is what you get. So one last thing that I will talk about is some two important theorems, the divergence theorem and the Stokes theorem. I'm sure you know about that, but just a quick revision of that. So suppose you have a volume which is bounded by this surface. So there's one S0 surface, and inside also you have these voids, let's say. So you are interested in only the remaining portion apart from the void. So this is your volume. This is some given volume V. And you're performing an integral over divergence of some vector V in this volume. So this volume that you define, this integral that you're performing is in that. So the remaining at the surface, you can define a normal vector the way we are doing. So outside, it's always pointing outside, outward from the material side. So here, this is the domain of interest, so it's pointing outward. Now this portion has been excluded, so this is the material, so it's pointing this way, and this is in this surface is pointing this way, and here it's pointing this way. So your volume V is bounded by some surface S0 and a lot of these surfaces which are voids within the volume S1, S2, and S3 surfaces are there. So you can, divergence theorem says that the divergence of the integral of the divergence of quantity is same as if you take the flux on the surfaces v dot n ds. This is for any vector field, you can write it this way. And this flow on a closed surface, of course, closed surface which is bounding the volume. N is the normal at the surface. So sometimes you will see this written as ds vector, where ds essentially is n, the normal at the surface, times the small area. So you can split this second integral that you have on the right hand side, this integral, into integrals over different surfaces like S0, S1, S2, and so on. In all cases, n, you have to see that it's pointing away from the volume that you're interested in. This is the divergence theorem. I'll not get into the proof of this. Stokes theorem is also interesting. It relates the surface integral of a curl of a vector with the line integral which is bounding the surface. So suppose if you take the surface as this quantity, this is a surface, and you can think of it as a hollow surface which has been cut by this plane, cut by a plane which, and this is the boundary of that surface now. So now, if you're performing an integral on this of the curl of V, then essentially the curl of V is given by this. So if you have a, when you're doing this integral, so you are essentially doing curl of V defining on this, and at the end, these if you have a continuous, V is continuous, then variation, then here it will cancel out, because here, as you can see, in this side it's going in this way, so then now the small area next to it will go like in this fashion. So the sense of rotation remain the same, but then they will cancel out, and only thing that would be left would be the boundary. That's uh, the concept behind the Stokes theorem. So the curl of V dot in ds would be essentially this something called circulation. If you take the quantity defined at the bounding curve now, closed curve now, this should be a closed curve, of course, it will be V dot dl. So that gives you the Stokes theorem. So this is with what, I mean, I'm not going to get into the proofs of these, but maybe I'll include one or two problems, because these divergence theorem and Stokes theorem are extremely important in engineering applications. So yeah, with this we'll finish this part of the course. On this part of the course, this is called linear algebra. So